This lesson is on the graphs of the secant and cosecant functions. Be sure before you do this lesson that you know how to graph a sine and a cosine function really well. That means that you understand how to adjust the periods of those functions and do any vertical or horizontal shifts that are involved, and that you understand what happens with the amplitude. We're going to actually start by looking at the graph of y equals cosecant x. Now, we have generally on these lessons started out by looking at a table of values for the function. So I want to look at this table of values that I have started for you, and if you notice up here I have reminded you that the cosecant of x is also equal to 1 over the sine of x, and I used this to help us with this table of values. For instance, at pi over 6, which is like your 30-degree angle if you think in terms of degrees, we know that the sine of 30 degrees is 1/2, don't we? So if x is pi over 6, the sine of pi over 6 is 1/2. 1 divided by 1/2 becomes a 2, doesn't it? In other words, if you take the value of the sine function at these angles and just simply flip them upside down, you'll have the values of the cosecants. Remember, at pi over 4, of course, if you rationalize it, it looks like square root 2 over 2, but before you rationalize it, it's 1 over square root 2, so when you flip it, you get a square root of 2. And so on, and you'll notice that, of course, when you flip a 1, you still have a 1, so where the sine is 1, the cosecant is also 1. You will notice that I have not put any values here at 0 or at pi. Also, notice as I continued here, when we got over into the third and fourth quadrants, if the sine function becomes negative, so does the cosecant, because when you flip a negative, it's still negative. But I've also got a blank here. Let's talk about those specific points. What is the value of the sine function at x equals 0? Well, the sine of 0 is what? It's 0. Can we have 1 over 0? No, we cannot. At x equals 0, at x equal pi, and at x equal 2 pi, the sine function becomes 0, which means that the cosecant is undefined at those places. Now, we're not going to necessarily just plot these points, but I wanted you to look at them and be thinking about where those values came from as we look at how to approach the graph of the cosecant function. What we're going to do here is to graph what we call a guide function to help us out. Now, this is not the graph of the cosecant yet. My guide function is going to be the reciprocal of cosecant, which is the sine function. In other words, I'm going to graph y equals sine x as a guide function to help me graph cosecant. Let me show you how this works. Now, we know all about the sine function. Remember our specific values at 0, at pi, which is a little more than 3, we're on 0. At 2 pi, which is a little more than 6, we're on 0. Halfway between here at pi over 2, we're on 1. And halfway between these at 3 pi over 2, we're down on -1. Now, I'm not going to make that a solid graph, but I'm just going to kind of dot those values in. Now, this is just one period of my sine function. We know that this graph would continue. I'll just put a little bit of a continuation here, and it would keep going in both directions. We have already noted at these places where the sine function is 0, the cosecant is not defined. If you recall, when you looked at tangent functions in our video on the tangent function, when the function became undefined, we had asymptotes there. And actually, you could use your calculator as well, set in the radian mode, and if you plugged in some numbers very close to 0 but not quite there, like maybe 0.001 or whatever, you'd find out that your cosecant values would increase greatly because your sine values are getting real small, and when you invert them, they become large. Now, what I'm doing is, after I graphed this guide function, you'll notice I'm putting in vertical asymptotes at every place that my guide function is crossing the x-axis, because that would be the places where our y value is 0. So if the y value is 0, if sine is 0, cosecant, which is 1 over sine, is undefined there. Now, here's how we're going to graph this. Right here, the value of the sine function is 1, and if you invert a 1, you still have a 1. Right along in here somewhere, the value of the sine function is 1/2. If you invert a 1/2, you get a 2. Similarly, right over here somewhere, the sine value is 1/2. If you invert it, you get a 2. What happens is, as these fractions get smaller, when you invert them, their values get larger. So the actual cosecant function will approach these vertical asymptotes. It will share this value of 1 with the sine function here, because when you invert a 1, it's still a 1, but otherwise the fractions, when they're inverted, become large. Okay? Now, over here, our sine values are negative, consequently our cosecant values are negative. If I invert a -1, it's still -1. Note that if you invert a -1/2, you get a -2. Here you're going to have another -1/2 that's going to come down here as a -2. So these values will do something like this. Notice as you get real close to the y-axis, if you have a -1/10 for the y value and you invert that, you get a -10. This part right here and this part right here is the actual graph of the cosecant function. This dotted y equals sine graph we're just using as a guide function. Now we have graphed one period of the cosecant function. Notice that when the sine function comes back over here and crosses, we're going to have another asymptote here. Because these are negative, we'd have another part of our cosecant function being here. As the sine function comes back up, we'd have another part over here. So you will see these things being repeated, of course, forever. It is periodic. But notice that all the way from 0 to 2 pi is needed to get a complete cycle of this cosecant, because we have not only this part, but we also have the negative part. So one period of this cosecant function is going to be 2 pi. Now I might ask you, since we use the sine function as a guide function, and the sine function has an amplitude, remember, of 1, does the cosecant have an amplitude? Well, the answer is no. It does not have amplitude. Do you know why? Remember, amplitude again is maximum minus minimum divided by 2. Does the cosecant function have a maximum? No, it does not, because that keeps going on up. Does it have a minimum value? No, because that keeps going on down. These do not exist for the cosecant, so there is no amplitude. The only trig functions that have what we call amplitude are the sine and the cosine, and that's because the sine and cosine are the only ones that are always restricted between a high and a low point, and the graph never goes beyond those. So your tangent, your cotangent, your secant, and your cosecant do not have amplitude. Okay, well, let's graph y equals the secant of x. And I have done a similar process here. If you'll notice, I've done a table of values, but I've reminded you that the secant is 1 over the cosine. Remember, at 0, the cosine is 1, so 1 over 1 is 1. At pi over 6, the cosine is square root 3 over 2. If you invert that and rationalize it, you get this. And so on. At pi over 3, the cosine is 1/2. If you invert that, you get a 2 for the cosecant, or for the secant rather. What happens to the cosine at pi over 2? Well, at pi over 2, the cosine is 0. 1 over 0 is not defined. Remember, at pi, the cosine is -1. If you invert a -1, it's still -1. What happens at 3 pi over 2 for the cosine? It's back on 0, so 1 over 0 again is undefined. So much like what we did with the cosecant function, we're going to do with the secant function. But this time, our guide function that we're going to use is going to be y equals the cosine of x. Now let's remember that the cosine starts at 0, 1. At pi, the cosine is on -1, and at 2 pi, the cosine is back up on 1. And of course, halfway in between, at pi over 2, it's on 0. At 3 pi over 2, it's on 0. So again, I'm going to just kind of dot in this little guide function. Okay? And again, of course, we would have other periods of this cosine graph. Okay. Everywhere that the cosine becomes 0, which would be here and here on our graph, as we learned before, we will have an asymptote because 1 over 0 is undefined. Notice right here, if the cosine is 1, if you invert a 1, you get a 1. When the cosine is 1/2, when you invert, you get a 2. So much like the secant graph, the cosecant graph, the secant is going to sort of come off and do the same thing. If you invert a -1, you get -1. If you invert a -1/2, you have a -2. Same thing over here. So this part is going to do this. If you invert a 1, you have a 1. If you invert a 1/2, you have a 2. So it's going to come like this. Now this shows one period of the secant function. Now if you'll notice, we've got sort of a half of a cycle here and another half here. That's because if we look at one period of the cosine going from 0 to 2 pi, these are the pieces of the secant function that we get. Keep in mind, as the cosine continues here, we would have another asymptote, and this part of the function would come back on up there, and this part would continue up over here. So again, it's going to look a lot like that cosecant graph, but as you can see, there's been sort of a shift in terms of its location. Notice again, the period is 2 pi. So the secant and the cosecant have the same period as the sine and the cosine, 2 pi. The only trig functions that don't have 2 pi as a period are the tangent and the cotangent. Okay? Now that we have looked at the basic graphs of secant and cosecant, let's look at the general secant and cosecant functions. Because just like all of the other trig functions, we can have all these other numbers appearing in our equations. Notice we can have a number in front of the function like we did with sine and cosine and tangent and cotangent. We can also have a complicated looking argument of our function. And of course, what does this plus d thing do? It causes a vertical translation, doesn't it? The C causes us a shift left or right. The B changes the period, just like with the others. Notice, to get the period, you take 2 pi, which is the original period of secant and cosecant, and you divide by b, which is the number times x. Do you notice how we're always consistent with that? To find the period of any trig function, you take its original period and divide by any number that's multiplied times x in the argument of that function. Notice I've said graph the corresponding reciprocal function as a guide using a dotted curve. So the corresponding reciprocal function, if you invert a secant, what do you get? You get a cosine. If you invert a cosecant, you get a sine. So that's what we mean by the corresponding reciprocal function. Now, let's see how we can apply this general information to a little bit more complicated equation than we started with. We want to graph y equals 2 times the secant of 3x. So right here, I'm going to talk about my guide function. I'm just going to write basically the same equation, except I'm going to say the reciprocal of a secant is a cosine. So I'm going to graph y equals 2 times the cosine of 3x, and I'm going to use that as my guide function. Okay, well, let's talk about this cosine 3x. Notice, first of all, I have something times x, don't I? So the period is going to be the original period 2 pi divided by 3. Okay? What's the 2 going to do? Amplitude of my guide function is going to be 2. Now, do I have any kind of a shift? No, I don't. Let's take this argument of 3x, and remember, with the sine and the cosine, we place that between 0 and 2 pi, and we solve for x. So if we divide by 3, we get 0 is less than or equal x is less than or equal 2 pi over 3. That tells us our period is going to start at 0, it's going to stop at 2 pi over 3, which is a distance agreeing with our period. Now, as we've done before, we want to be sure that we sort of keep this on a good scale. So you might want to calculate 2 times pi divided by 3. That's about 2.1, okay? 2.1, about right here, okay? So we're going to start here, and we're going to stop right now. Now, this is going to be a real small little graph, isn't it? We're beginning at 0. We're stopping at 2 pi over 3. What's halfway between there? Well, half of 2 pi over 3 is 1 pi over 3, isn't it? How much is pi divided by 3? Well, it's just barely bigger than 1, isn't it? Okay, so about right there, okay? Now, if we need the little points halfway between here, half of pi over 3 is pi over 6. And if we want the halfway point here, we'll add these together, and we get 3 pi over 3 times a half is 3 pi over 6, or pi over 2, okay? So, of course, we can sort of estimate those values roughly here and here, okay? Now, we have an amplitude, remember, of 2. This is a cosine function. So on 0, we're going to be up on 2, and we're going to come down. Notice I'm just kind of dotting this in. Halfway in between our period, we're going to be down on -2. We'll kind of dot that in, come back up. At the end of our period, we'll be back up on 2 because of that amplitude. Okay? So there's my guide function. Now, all I have to do to get the graph of this secant function is to note these places where my guide function is crossing the x-axis, because we're saying at these values right here, this cosine function becomes 0. Okay? So, at those places, we're going to have a vertical asymptote. Okay? And then, at this high point right here, we're going to flip off of that. Notice as these fractions flip, they're going to get bigger, so we're going to go up to this asymptote right here. I'm going to go ahead and do this side. From this 1, we'd go up, see, as we approach toward the left there, because these fractions would invert and get bigger. And then from this low point right here of -2, we're going to flip over and come down like this. Okay? So do you see how we're using the guide function? Where we cross the axis is where that guide function becomes 0, and therefore that's where our asymptotes will be. Well, let's try this one. Y equals 5/2 times the cosecant of x minus pi over 4. Okay, what is our guide function going to be? Well, our guide function is going to be y equals 5/2. What's the reciprocal of cosecant? It's the sine function. So 5/2 times the sine of x minus pi over 4. Okay? What is the period going to be? Well, the original period is 2 pi. Do I divide by anything? No, I don't. Notice there's just a 1 times x. There's not any other number times x. So our period will stay at 2 pi. What is the amplitude of this guide function going to be? It's going to be 5/2. Okay? Of course, this is going to cause us to shift, isn't it? Let's take this argument, x minus pi over 4, and put it between 0 and 2 pi. Now, when we add pi over 4, we get pi over 4 is less than or equal x, is less than or equal 2 pi would be 8 pi over 4, so if we add one more, we have 9 pi over 4. Notice between pi over 4 and 9 pi over 4 is a distance of 8 pi over 4, or 2 pi, which agrees with our period. Okay, so we're going to begin this graph at pi over 4. We will end it at 9 pi over 4. Let's get the midpoint. If we add these, we have 10 pi over 4 divided by 2, or times a half, gives us 5 pi over 4. Okay, let's go ahead halfway between these. If we add 6 pi over 4 divided by 2, or take a half, is 3 pi over 4. And finally, halfway between these, if we add these, 9 and 5 is 14 pi over 4. If we take half of that, we get what? 7 pi over 4. Okay, so pi over 4 is going to be close to 3/4. Okay, let's go ahead and get that end value. 9 times pi divided by 4 is about 7.1. 3, 4, 5, 6, 7. So it's going to be about where this little arrow thing is. And 5 pi over 4 is about 3.9. So almost 4 is our midpoint. 3 pi over 4 is about 2.4. Okay. And finally, 7 pi over 4 is about 5.5. About 5.5. So there's our little markings. Now, this is a sine function. So we start at 0, we're on 0 in the middle, and we end at 0. If our amplitude is 5/2, that's what, 2.5. So halfway between here, we're going to be at 1, 2.5. So let's kind of dot that in. And then halfway between these, we're going to be down 2.5. Okay, there's our guide function. Okay, notice it's been shifted over, amplitude 5/2. I might mention while I'm thinking about this, this amplitude is the amplitude of my guide function. It is not the amplitude of cosecant. Remember, the cosecant itself does not have amplitude. Now again, this guide function is crossing the x-axis at these points. That's where the guide function becomes 0. So if you invert it, it becomes undefined. So those would be the places that we would have vertical asymptotes. Okay, from this high point here, we're going to go up, and from this point here, we're going to go down. Okay? Now, let me just mention here, I went ahead and included this 5/2, and you may be thinking, well, if you have 2.5 or 5/2 and you invert it, that's 2/5. Why wouldn't it be down here? Well, here's the deal. Keep in mind the 5/2 is times the cosecant. If the sine function were 1, then the cosecant would be 5/2 times 1. Okay? So we just use that amplitude to help go ahead and move us up. So in other words, the value of the sine function is going to be multiplied, or after you invert it, it's going to be multiplied by 5/2. And so if you go ahead and do the amplitude here on this sine function, it just kind of moves all that up for you and takes care of that stretch for you. I have one other example that I would like to do for you. Graph y equals cosecant quantity 2x minus pi minus 1. What's that little guy going to do? That's a vertical translation, isn't it? That's going to move us down. Okay, we're going to include that when we write the guide function. So let's write our guide function. Have you noticed that on my guide function, I'm pretty much leaving everything the same. I'm just changing to the reciprocal function. So sine 2x minus pi minus 1. Now, the period, let's look at that. The original period of a sine function is 2 pi. Do I have anything times x? Yes, I do. I have a 2 times x, so we'll divide by 2 and we'll get pi. The amplitude on this one is 1. Notice there's no number here. Let's look at taking the argument 2x minus pi and putting it between 0 and 2 pi. If we add pi, we get pi is less than or equal to 2x. If we add pi here, we get 3 pi. Finally, divide by 2. Pi over 2 is less than or equal x is less than or equal 3 pi over 2. Notice from pi over 2 to 3 pi over 2 is a distance of 2 pi over 2, or pi. So we are in agreement there. Okay, we're starting at pi over 2. We're stopping at 3 pi over 2. Okay, if we add these together, we get 4 pi over 2. If we take half of that, we get 4 pi over 4, or pi. Okay? Halfway between these, this is 2 pi over 2, so 3 pi over 2 times a half, 3 pi over 4. If we add these, 2 pi over 2 plus 3 is 5 pi over 2 times a half is 5 pi over 4. Okay? So we know pi over 2 is a little bit more than 1.5. Okay? And of course we know where pi is. That's just a little bit beyond 3. That's our halfway point. 3 pi divided by 2 is about 4.7. 1, 2, 3, 4.7. So about right in here is going to be the end. And I'm just going to kind of estimate halfway between there and halfway between there for now. Keep in mind this vertical translation. What does that mean we're going to do? We're going to move everything down 1. So let's just bring these points that we found down 1. Okay. it's a sine graph, amplitude 1. Now remember, this is just a guide function, so we start here, go up, come down 1, back up. So there's our little guide function. Now, remember when you do the translation, basically what you're indicating is that it's kind of like you've moved your x-axis down 1, in a sense. So these places right here where we have moved down 1 are the places that we want for our asymptotes. Okay, and then just like we've done before, from this high point we're going to flip off of that, go up. From this low point we're going to flip off of that and go down. And so here and here will be one period of this cosecant graph. I think you can see that if you are pretty good at graphing sines and cosines, you can do the secant and cosecant pretty easily. If you still struggle with sine and cosine, then you're going to struggle with this also. But just keep in mind, use that correct reciprocal function as a guide function, and you're looking for those places where that guide function crosses the x-axis as your asymptotes. But remember, if there's a vertical translation, and when you move it up, then you're looking at crossing that new horizontal line where you've moved your x-axis to in the sense. Okay? I hope that this lesson has helped you in graphing your secant and cosecant function.